Okay, so last time we looked at graphs like this and we learned that they can represent actual things. So like displacement in meters over time in seconds. So this would be a displacement versus time, or a position versus time graph as they call it. Notice I did away with all of the left side of the y-axis because we don't have negative time. It's a scalar. It only goes in one direction, forward. But we still need a positive and a negative of displacement because meters can go backwards or forwards away from an origin point. Okay? We also learned that if you have a line on a displacement versus time graph, then you can find the slope doing rise over run, and that's going to give you a velocity that's measured in meters per second. That's what your slope is going to be of a line like that. Well, we need to translate that over because it doesn't end with displacement versus time. You can graph velocity versus time. In fact, I've done that just over here. And as you can see with this velocity versus time graph, that you just replace the distance or displacement with velocity, and this time it is meters per second. And time is still in seconds. Time's still only going to go in one direction. Looks like I lost one of my time units there, but that's okay. Okay, so we can also find the slope of a line on this graph because now I have velocity, which has negative and positive values, over a time, and I can get a new slope. So if I do the slope here, I'm going to do my rise over my run. Notice that the rise is velocity this time divided by time, or meters per second divided by seconds, right? Because those are the units. Well, what happens when we do velocity divided by time? We get an acceleration. And remember, acceleration's units are meters divided by seconds, or more appropriately, meters per second squared, right? And that's all that this is showing you there. So if we have a velocity versus time graph like we do here, then our slope is going to give us an acceleration. And so that's another data point that we have, and we can use this in order to solve, again, like we do the same equation we did before, the equation for a line there, except this time our slope would be acceleration. And all of this works in conjunction. In fact, we can look at both of these graphs together, and we can say, I can determine where my velocity is over a given time by where my line is telling me my readings for my position versus time. So basically I just figure out what the slope is at each second mark. So the slope of this line isn't going to change, so it's going to be the same throughout. So if we determine its slope, we'll figure it out pretty easily. And it looks like it goes up 2 and over 2 every time. So that would be a slope of 1. Well, that just means that we can put data points on, and we see at 2 seconds, it's at 1. At 4 seconds, it's at 1. At 6 seconds, it's at 1. At 8 seconds, it's at 1. And so on and so forth. So that means that what we're really saying is that these two graphs now tell us the exact same thing. Okay? We're saying that this graph, the displacement versus time, its slope shows us velocity. And that velocity, we can see how it changes over time. With that, we create data points based on the seconds, and we get that the velocity doesn't change. Otherwise, it's a constant velocity, and that's why you have a nice straight line that's horizontal, because a non-changing velocity doesn't have acceleration, and it's just going to be a nice straight flat line to the side like that. But there's one more thing you probably need to know. What you need to know is that straight lines aren't the only kind of lines you find on a graph. In fact, a lot of times you'll find a curved line like this one. Now I know it's crudely drawn, but it's a curved line. And the thing is, this shouldn't need to scare you. You're not going to have to calculate this. You just need to understand the trend. And this is the fact that it has a changing slope. as you go to this different point, so I have some different points marked on it, so like at the 2-second mark, it's going to have a different slope than at the 4-second, and a different slope at the 6-second, and a different slope at the 8-second. And so what you would do is you draw a tangent line to that point, and you get an idea of what that slope is going to be. So let's do it in yellow here. If I was drawing a tangent line to the slope right there, it might look something like that. But then if I did a tangent line, we'll do this one in blue, to this slope, it might look more like that. And then if I did a tangent line to this next one, it's going to be even sharper. And what you can tell about these, that as you increase these lines, or as you change these lines, as you do the slope is getting steeper and steeper. And that's what you really need to notice, is that we're increasing the value of the slope. So on a displacement versus time graph like this, if the slope is changing, so the line is curved upwards, then that means that you're going to be increasing your slope. Your slope is going to be increasing, which means your velocity is going to be increasing. So your velocity is increasing as it moves along. So it's not a constant velocity anymore. That also means that this line has an acceleration, because it's not a constant velocity. It's a changing velocity, a changing slope, changing velocity, which is an acceleration. Okay, the same thing would work if we had a downward curved line. Okay, so let's take a look at that. So now I have a downward curved line. And if a downward curved line, we still have some points we can look at. You might draw a tangent line, and you might notice that it's going to get less. So let's draw those tangent lines. Let's take a look at what we have. So this first one here, tangent line is going to be pretty steep like that. Our next one, it's going to be a little less. It would be like that. And then our third mark that I have here, we'll do that in green too. Look, it's even less. And so you can see that a downward curved line is going to have a decreasing slope. That means the velocity is going downward. It still has an acceleration. The velocity is still not constant. It's changing, in fact. And that means that it's going to be decreasing, because that tangent line to any given point is now going less and less and less of a slope. So less and less velocity. All right. So here we have the three types of graphs side by side, so that you can see that they affect one another. Because remember, our position versus time, or displacement versus time, is the slope of this line tells us velocity, and we can look at how that velocity changes over time, and we can mark that with data points. Remember that we said if it's a curve, then it has a type of acceleration. A downward curve is a negative acceleration. A upward curve is a positive acceleration, because you're changing your velocity and you're getting a less and less velocity. And then when you're going upward, you're getting a greater velocity, right? And so that shows here. There's a couple of things that are unique to these. For one, and let's see if I can click on it to move on it. Jumped around on me. So for one, if we're looking at these things, the position versus time graph, notice how I can move the starting point and it doesn't affect either of the two, velocity or acceleration. That's because a position versus time is the only one that can actually show us your starting point of motion. It's the only one that has the exact position that you begin in. Other than that, they pretty much say all the same things. So if you change one, you're going to change them all. For instance, if I change my velocity, you can see my position versus time and my acceleration changing. And I can do some pretty simple things. So let's try to give myself a constant acceleration, and that would be a straight line on here. It's not absolutely perfect, but you can see it a little bit. I can't get it absolutely. Okay, I'm going to move my position versus time down a little bit just so you can see it a little bit more. Now notice that this is an upward curving line, so it is a positive acceleration. That shows that, right? That's good. It's only one way that it's curving, so there's only one acceleration. We said that it would have gradually increasing velocities. Well, look, this is gradually increasing in the amount of velocity that it has. And then our velocity versus time, if you measured this, you would get one acceleration, and it would be a positive acceleration, and that's right here. So all three of these are going to give you exactly the same data, other than your position versus time has a starting point, an origin point. Look at one more example using this, and this time I'm going to probably put it up top. Let's see if we can do a negative velocity so that it's decreasing just a little bit more, and then right at the end we are going to go back up to positive. Okay, so if we do that, yeah, I know it's not super perfect, but it's enough for our example. And then I'm actually gonna, I can't bring that up high enough to see it. Okay, so in that case, let's just forget about that one. Let's say it's down there too. All right, so if you look at this one, this is a downward curve, which is a negative acceleration. And it should be a pretty straight line. I ran out of room, so it's a little messed up, but notice it's pretty constant in that acceleration. And if you measured this, it would have a negative slope, negative acceleration. This would be a changing negative value for each of the tangent lines here, and that would be a changing negative value here. So that's how they all work together. I hope that helps.